Hello, in this lecture we will find the area of the yellow circle. Uh, you can see in the drawing a semicircle. The center of the semicircle is at point O, and inside the semicircle we have the yellow circle, and the size of the line segment PQ equals to 7 times root 2, and the touching point between the yellow circle and the semicircle is at point P, or the point of contact between the yellow circle and the semicircle is at point P. So let's define the center of the yellow circle as M. So the center of the yellow circle is at point M, and let's connect points M and O together by a straight line. So actually the line segment MO is the radius of the yellow circle, because it starts from the center of the yellow circle and ends at point O, that is a point on the yellow circle itself. For that reason, MO is defined as the radius of the yellow circle. I will mark it as small r. In general, the definition of radius is any line segment that starts from the center of the circle and ends at any point on the circle is defined as the radius. And the line segment MO starts from the center of the semicircle, that is to say from point M, and ends at point O, that is a point on the yellow circle itself. For that reason, line segment MO is the radius of the yellow circle. Okay, so actually we have a rule. I will call it rule number 1. And rule number 1 states that if two circles touch each other, either internally or externally, then their point of contact lies on the straight line joining their centers. So I will read again rule number one. Rule number one states that if two circles touch each other either internally or externally, then their point of contact lies on the straight line joining their centers. So actually the yellow circle touches the semicircle at point P. Point P is the point of contact, and actually rule number one states that the point of contact, that is to say point P, lies on the straight line joining their centers. So point P lies on a straight line. Which straight line? The straight line that joins the centers together. So we have two centers. Point M is the center of the yellow circle and point O is the center of the semicircle, and the line segment that joins the centers together is the line segment MO. And actually rule number one states that point P is actually on the same straight line. Okay, point P is on the same straight line of MO, of the line segment MO, or in other words, PMO is a straight line. Okay, so we can say that PMO is a straight line. Or in other words, if we connect together points P, M and O by a line, then that line will be a straight line. Okay? Okay, so actually the rule number one states that if two circles touch each other in our state, in our drawing, the yellow circle touches the semicircle at point P internally, and rule number one states that their point of contact, that is to say point P, lies on the straight line joining their centers together. So the straight line that joins the centers together is actually the straight line MO, and rule number 1 states that point P lies on the same straight line as MO. So point PMO are on the same straight line, or PMO is one straight line. Okay, or in other words, if we connect together by a line points P, M and O, then that line will be a straight line. Okay, or we can also say that PO is a straight line. Okay, again, if two circles touch each other, that is to say the yellow circle touches the semicircle at point P, then their point of contact, that is to say point P, lies on the straight line joining their centers. So point P lies on the straight line that joins the centers together, and actually line segment MO joins the centers M and O together, and according to rule number 1, point P lies on that straight line. Point P lies on the same straight line as the line segment MO, or in other words, PMO is one straight line. And again, if we join points P, M and O by a line, then that line will be a straight line. So PMO is a straight line. Okay. So if two circles touch each other internally or externally, then their point of contact, that is to say point P, lies on the straight line joining their centers. So point P lies on the same straight line as the line segment MO that joins their centers together. Point P lies on the same line segment that joins their centers together, or the same straight line as the line segment MO that joins their centers together, or in other words, PMO is one straight line, or we can say that if we draw, or if we connect the points PM, and O by a line, then that line will be a straight line. So PMO is a straight line, or we can also say that PO is a straight line. Okay, so the line segment MP is also the radius of the semicircle. I will mark is the radius of the yellow circle. I will mark it as small r. Again, the line segment MP is the radius of the yellow circle, and I marked it as small r. So actually PO equals to 2 times the radius of the yellow circle. PO equals to 2 times the radius of the yellow circle. That is to say, PO equals to the diameter of the yellow circle. because any line segment in the circle that equals to 2 times the radius of that circle is defined as the diameter of the circle. So PO is actually the diameter of the yellow circle. But because of the fact that PO is a straight line, we can also say that POP equals to the radius of the semicircle, because it starts from the center of the semicircle, that is to say from point O, and ends at point P, that is a point on the semicircle itself. So OP is the radius of the semicircle. I will mark it as capital R. Okay, the radius of the semicircle equals to capital R, while the radius of the yellow circle is marked by a small r. Okay, so we can write down that PO equals also to the radius of the semicircle. So actually we have here two equalities. PO equals to 2 times the radius of the yellow circle. That is to say, PO equals to the diameter of the yellow circle from one side, but from the other side, PO equals also to the radius of the semicircle. So we can write that PO equals to PO, and then we can substitute PO by capital R from this equality, and we can substitute PO by 2 times small r from this equality, and we will get that capital R equals to 2 times small r. So this is our first equation. Capital R equals to 2 times small r. Our first equation is that capital R equals to 2 times small r, or the radius of the semicircle is twice as big as the radius of the yellow circle, or the radius of the semicircle is larger twice than the radius of the yellow circle, or the radius of the semicircle is bigger twice than the radius of the yellow circle. Okay, so we can also say that OQ is the radius of the semicircle, because line segment OQ starts from the center of the semicircle, that is to say from point O, and ends at point Q, that is a point on the semicircle itself. So for that reason, it will be defined as the radius of the semicircle. I will mark it as capital R. So we have here two radiuses of the semicircle, PO and OQ, and actually we have also rule number 2 that states that in any circle a radius and the tangent to that radius are perpendicular to each other. Okay, I will read again rule number 2. Rule number 2 states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So actually, if we have a radius, let's call it R, and a tangent to that radius, let's call it T, then the radius is perpendicular to its tangent, that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in any circle, the radius and the tangent to that radius are perpendicular to each other. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So actually we can implement rule number 2 in our circles because we have the radius of the yellow circle, line segment MO is the radius of the yellow circle, and we have tangent QO to that radius. So according to rule number 2, the radius is perpendicular to its tangent. So the angle POQ will be equal to 90 degrees. Because of rule number 2 that states that in any circle the radius and the tangent to that radius are perpendicular to each other. So the radius, line segment MO is the radius, is perpendicular to its tangent. So angle POQ equals to 90 degrees. Okay, so in any circle, the radius and the tangent to that radius are perpendicular to each other, that is to say angle POQ equals to 90 degrees. So actually, triangle POQ is a right triangle because angle POQ equals to 90 degrees. So actually, we can implement here the Pythagorean theorem in order to find out the value of capital R. First of all, I will draw again the right triangle POQ. So this is the right triangle POQ. As you can see in the drawing, side PO of the right triangle POQ equals to capital R, and also side OQ of this right triangle equals to capital R, and the hypotenuse of the right triangle POQ equals to 7 times root 2. And actually the Pythagorean theorem apply only to right triangles. So I will write down the Pythagorean theorem, and then we will implement the theorem in our right triangle in order to find out the value of capital R. Okay, so actually the Pythagorean theorem states that so as I've already told you, it applies only to right triangles. So in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I will read again the Pythagorean theorem. The Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, if we have right triangle A, B, C, so the Pythagorean theorem states that the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars, that is to say equals to AB square plus BC square. Okay, the square of the hypotenuse AC square equals to the sum of the squares of the perpendiculars, that is to say equals to AB square plus BC square. Okay, so we can implement this rule in our triangle, and actually the square of the hypotenuse is actually PQ square. This will be our second equation. Equals to the sum of the squares of the perpendiculars, that is to say equals to PO square plus OQ square. So equation number 2 is PQ square, that is the hypotenuse, equals to PO square plus QO square. Okay, but we know that PQ equals to 7 times root 2, PO equals to capital R, and OQ equals to capital R. So we can put the data in the second equation. So we got that 7 times root 2 square equals to R square plus R square. PQ equals to 7 times root 2, so we substituted PQ by 7 times root 2. PO equals to capital R, so we substituted PO by capital R, and OQ equals to capital R, so we substituted the OQ by capital R. Okay, so 7 times root 2 square equals to 49 times 2, and R square plus R square equals to 2 times R square. Okay, so I write it down. Seven times root 2, actually 7 square is 49, and root 2 square is equals to 2. R square plus R square equals to 2 times R square. Here we can divide the equation by 2. So we divided the equation by 2, we got that 49 equals to R square. Now we can take a root out of equation number 2 here. We will get that the root of 49 equals to 7, the root of R square equals to R, so capital R equals to 7 units. Actually the root of 49 is also negative 7, but because we are dealing with radiuses, radius must be a positive number, so we will take into account only the positive root of 49, so actually the capital R equals to 7 units, but according to equation number 1, capital R equals to 2 times small r. So we can write it down. Okay, capital R equals to 2 times small r, according to equation number 1. So we can substitute r by 7 in equation number 1 because capital R equals to 7. So we substituted r by 7. We got that 7 equals to 2 times r in the first equation. Now we can divide the equation by 2. So we got that small r equals to 3.5 units. So after we know the radius of the small circle, it is very easy to find out the area of the yellow circle because we have the formula for the area of any circle. The first equation will be the area of any circle equals to pi times r squared. Okay, the area of any circle, area A is the abbreviation for area. The area of any circle equals to pi times the radius squared. But we know that the value of the radius is 3.5 units according to equation number 1. According to equation number 1, the area equals to 3.5 units. So we can substitute r in equation number 3 by 3.5 units. We will get that the area equals to pi times 3.5 square. So we substituted r in the first equation by 3.5. We got that the area equals to pi times 3.5 square, and 3.5 squared equals to 12.25. So I write it down. So the area equals to pi times 12.25. The area of the yellow circle equals to pi times 12.25 because 3.5 squared equals to 12.25. So we got that the area equals to pi times 12.25. And the final answer is that the area of the yellow circle equals to 38.48 units. Okay, so pi times 12.25 equals to 38.48 units. So the area of the yellow circle equals to 38.48 units. The area of this yellow circle is 38.48 units. Okay, so now I will summarize the lecture. So actually we wanted to find the area of the yellow circle, and in the drawing we have the semicircle, and inside the semicircle we have the yellow circle, and the center of the semicircle is at point O, and the size of the line segment PQ is 7 times root 2. And the touching point between the yellow circle to the semicircle is at point P. Or point P is the point of contact between the semicircle and the yellow circle. So we actually defined point M as the center of the yellow circle, and we connected points M and O together by a straight line. That straight line is the radius of the yellow circle, and we actually have rule number 1 that states that if two circles touch each other internally or externally, then their point of contact lies on the straight line joining their centers. So actually the yellow circle touches the semicircle at point P. P is the point of contact, and according to rule number 1, the point of contact lies on the straight line joining their centers together. So point P lies on the straight line that joins the centers together. Line segment MO joins the two centers MO together, and rule number 1 states that point P lies on the same straight line as MO, or in other words, PMO is one straight line. Okay, point P lies on the same straight line as the line segment MO, or in other words, PMO is one straight line. Or we can also say that if we connect points P, M and O together by a line, then that line will be a straight line. PMO is one straight line. Okay, again, the rule number 1 states that the point of contact P lies on the straight line that joins the centers together. So line segment joins the two centers together, line segment MO joins the two centers together, and rule number 1 states that point P lies on the same straight line as the line segment MO, or in other words, PMO is one straight line. Or we can say also that PO is a straight line. Okay, so Uh, Actually, the line segment MP is also equals to the radius of the yellow circle, because it starts from the center of the yellow circle and ends at point P, that is a point on the yellow circle itself. For that reason, NP is the radius of the yellow circle. And as you can see, OP is a straight line according to rule number 1, and it is equals to 2 times the radius of the small circle. That is to say, OP or PO equals to the diameter of the yellow circle. Okay? That is for one side, but from the other side, OP, that is a straight line, according to rule number 1, is also equals to the radius of the semicircle, because it starts from the center of the semicircle O and ends at point P, that is a point on the semicircle itself. For that reason, OP is defined as the radius of the semicircle. So for one side we have PO that equals to the 2 radiuses of the yellow circle, but from the other side we know that PO also equals to the radius of the semicircle. So we can deduce from it that that the radius of the semicircle equals to 2 times the radius of the yellow circle. Or in other words, the radius of the semicircle is twice as big as the radius of the yellow circle, or the radius of the semicircle is larger twice than the radius of the yellow circle, or the radius of the semicircle is twice bigger than the radius of the yellow circle. Okay, so actually PO is the radius of the semicircle, and for the same reason OQ is also the radius of the semicircle, because it starts from point O, that is the center of the semicircle, and ends at point Q, that is a point on the semicircle itself. For that reason, OQ is also the radius of the semicircle. And we have also rule number 2 that states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So if we have a radius, we called it R, and the tangent to that radius we called it T, then the radius is perpendicular to its tangent. That is to say, this angle is 90 degrees and this angle is also 90 degrees. So we can implement this rule in our circles, because we have the radius, line segment MO is the radius of the yellow circle, and we have the tangent to that radius, that is QO. Okay, so according to rule number 2, the radius is perpendicular to its tangent. So angle POQ is 90 degrees, because in any circle the radius and the tangent to that radius are perpendicular to each other. So this angle is 90 degrees. Angle POQ equals to 90 degrees. So actually we have here right triangle. POQ is right triangle because angle POQ equals to 90 degrees. So I draw again the right triangle POQ. Side OQ equals to capital R, side PO equals to capital R, the radius of the semicircle, and side PQ equals to 7 times root 2. This is the hypotenuse of the right triangle. And according to Pythagorean theorem, we can actually find out the value of capital R, the radius of the semicircle, because actually the Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So if we have a right triangle, this right triangle ABC, then the square of the hypotenuse, that is to say AC square equals to the sum of the squares of the perpendiculars equals to AB square plus BC square. Okay, so AC square equals to AB square plus BC square. So, and the Pythagorean theorem apply only to right triangles. So we can implement this theorem in our right triangle, because in our right triangle we can say that PQ square, the square of the hypotenuse, equals to OQ square plus PO square, the sum of the squares of the perpendiculars. Okay, PQ square equals to PO square plus OQ square. Okay, but we know that PQ equals to 7 times root 2, OQ equals to capital R, and PO equals to capital R. So we can put the data inside the question number 2, and we got that capital R equals to 7 units. So the radius of the semicircle equals to 7 units, but according to equation number 1, capital R also equals to 2 times small r. As I already told you, the radius of the semicircle is twice as big as the radius of the yellow circle. This is the equation number 1. So in equation number 1 we can substitute the radius by 7, the radius of the semicircle by 7, because the radius of the semicircle equals to 7 units. So we can put 7 instead of capital R, and we got that 7 equals to 2 times small r, and after we divided the equation by 2, we got that the radius of the small circle, small yellow circle, equals to 3.5 units. And after we know that the radius of the yellow circle equals to 3.5 units, it is very easy to find out the area of that circle, because the area of any circle equals to pi times the radius squared. And we know that the area of the semicircle of the yellow circle equals to 3.5 units. So we can substitute R by 3.5 units, because R equals to 3.5 units. So we put in the third equation, instead of R, we substituted it by 3.5 units, and we got that the area of the yellow circle equals to pi times 3.5 squared, and 3.5 squared equals to 12.25, and pi times 12.25 equals to 38.48 units, or the area of this yellow circle equals to 38.48 units. Okay, thank you very much.